Hello students, this is Brock Skaggs. I'm going to make this video working through a position or displacement based problem using analytical methods. And so in further videos we'll also look at it using graphical methods as well to solve the same problem. And so our problem focuses around a very simple crane machine that you see a schematic drawn there in the top portion of your screen. We've got some dimensions here. I note all our length dimensions will be in feet. And so the problem really is that currently point D, which is at the very end of your crane here, is located 17.25 feet above the ground. So y sub d right now is equal to 17.25 feet. This corresponds to a cylinder length, and our hydraulic cylinder is acting here between points A and C of 5.21 feet. And so the operator is now wanting to raise point D to a vertical height of 22 feet above the ground and needs to know how much to, in this case, extend the cylinder in order to achieve that 22-foot height. And so that's what our solution is going to be. We're going to be able to tell the operator, hey, you need to extend the cylinder X units or X inches out in order to have the point D be 17.2, or excuse me, point D to be 22 feet above. And so how are we going to do this? Well, we're going to look at the geometry and see if we can't relate some lengths and some angles together in order to come up with this. And so the first thing I'm going to do is I'm going to zoom in on our picture here and start thinking of some of the known things we have, some of the links we have, and so forth. And so one of the things we can look at is this triangle here, the triangle being formed by points A, B, and C. And so I guess I'll take my blue pencil here and trace out that triangle. And so really one of the things we're after is this length of the cylinder right here, L cylinder. And that's not going to be a right triangle necessarily, but we can still use things like law of cosines, law of sines in order to obtain that value from it. We know one length of it at least right here. BC is 6.5 inches long. If you look at points A and B, points A and B are both defined, so we should be able to find the length of this line segment, AB. And so at this point we've got 2 out of the 3 links. Law of cosines might be able to help us if we can figure out now this internal angle here, that internal angle formed by ABC, where B is the corner point there. And so let's think about how we could determine that. Well, one thing we could do is look at a triangle formed here. So I'm making a right triangle here where AB is the hypotenuse. Here I would presumably know this leg here and this leg here, the horizontal and vertical legs, and I could figure out this angle right there. And so if I knew that angle, and if I also draw a horizontal line right here, I could also determine this angle, right? Because the sum of these two angles would have to be 90 degrees. And so I should be able to get this angle. And that would just leave this angle right here as the only angle left before I could use the law of cosines in order to figure out the length of the cylinder. Well, one way I could get that angle there is by relating it to the overall height that I'm trying to achieve. And so if I basically think of a much bigger triangle here and take a vertical here, excuse me, that's not real vertical on the screen, and come over here with a horizontal there and form this right triangle that's going to be forming here between point B, point D, and the horizontal and vertical legs there, I should be able to come up with this angle here. That's because I know the overall distance, y sub d, and I also know this distance right here, 5.25 feet, and so I should be able to find this vertical leg here. After finding the vertical leg, I could use something like the inverse sine in order to come up with that angle. And so that'll be the way we go. Really, I'll kind of work in a somewhat backward fashion here. And so I'll first start on the red triangle here that we're forming down below. And so I'll get my black pen out. We'll come down here. And first we're going to look at that red triangle. And so instead of trying to draw straight lines, let's just use OneNote's ability here. And so there's one leg of the triangle, and we'll get the horizontal and vertical leg here as well. And here we are. So with this triangle, the bottom right point is going to be point B, the top right is D. So let's go ahead and mark these points here so we'll remember where we're at on the mechanism. And so this was B down here, got D up here. We know this is 24 feet right here. And really what we're after is this interior angle right here. We'll call it theta 1. And so how do we determine theta 1? Well, we need to know one of the side lengths here. And so one of the side lengths we can get to is this guy right here. This should be our y sub d value that we're trying to achieve. So in this case, the 22 feet minus this vertical offset here, minus the 5.25 feet that you see here. And so this vertical leg here will be 22 minus 5.25. That would get me to what, 16.75, I believe. Yeah, 16.75 feet there. I'm spending a lot of time coming up here, so give me 1 second. I'll just remove that so that those always stay there. And we'll go like this. And so this is 16.75 feet here. So at this point, I know the opposite side and the hypotenuse, so inverse sine should be able to help me. And so I'll just come right below here and say, okay, theta 1 is equal to the inverse sine. That's opposite over hypotenuse, so 16.75 feet all over the 24 feet here. And we'll compute our angle. That looks like 44.26 degrees. Okay, so now that we have theta 1, if we go back to our drawing at this point, we've got the red angle there that you're seeing, also this little green angle that I've got there. And so we called that theta 1. So as far as theta 2, let's work on the triangle formed by AB being the hypotenuse, and it's got that vertical and horizontal legs being green there. And so that'll be another triangle. I'll work on it here to the right a little bit. And so again, we'll just have one note to help us draw some straight lines here. Okay. And so the bottom left point is point A in this triangle that we've taken out. This is point B. And then we need to find the side lengths here as well as the hypotenuse eventually. So the vertical leg here, it'll be the 5.25 feet minus 3.75 feet from the drawing there. So 5.25 feet minus 3.75 feet here. I believe that's 1.5 feet for that. And the horizontal leg, 8.25 minus 4.75. So 8.25 feet minus 4.75 feet. That's one I'll just enter into the calculator. 3.5 feet. And let's also find AB while we're at it. And so AB, we can compute the hypotenuse just using Pythagorean theorem. I'll put 1.5 feet squared plus 3.5 feet squared all under our radical. Looks like 3.81 feet there. Alright, so everything's falling out nicely up to this point, and we needed an angle from this triangle. Now if you come back here to our plan, we needed that top right angle there, and so let's call that theta 2. We'll just increment the subscript of theta as we work along here. And so this angle here is theta 2. Here we can use a number of different inverse trig items here. I'll just use inverse tan, so we'll say theta 2 is equal to the inverse tan opposite over adjacent, so 3.5 feet divided by the 1.5 feet. should get us that angle. And it performs nicely. It looks like that is 66.8 degrees there. And so again, going back to our road map, if you will. Oops, I zoom in here. We have this angle here, represented by that arc there, is the 66.8 that we just calculated. We know this angle here from the beginning, and so now we're ready to calculate this angle before we move into our first blue triangle that we drew, that we can then apply law of cosines to figure out the length of the cylinder. And so we can work on this triangle here. The one item we can add to it is just a reference line here. Just to make sure we know it's not part of the triangle, I'll just make it dashed for us. And what we're really after is this theta 3 here. And so if you look at this, the dashed line is horizontal, this line here is vertical. We've got a 90-degree corner there, so theta 3 will just be the complementary angle of theta 2. And so to obtain theta 3, we'll just say theta 3 is 90 degrees minus theta 2. And just do a little bit of simple arithmetic here in order to arrive at 23.2 degrees for theta 3. And so we've got theta 3 now. And so now really to the kicker is this triangle ABC, because we know we're after the length of the cylinder at that extended state. And so again, I'll just draw a simple triangle down here. Notice both the triangles we've drawn at this point are both right triangles. I've had a 90-degree angle in there. This one's most likely not going to have that. And so I'll just come down here. These angles, of course, aren't going to be exact, but we will fill in the variables to represent the values. Okay. And some labels for us, A, B, and C, just to make sure we are able to track it here. Have my pin, and this is going to be A, this will be B, and we have C up here. So first things first, what do we know about the side lengths? Well, the length between B and C is 6.5 feet. And so we know this to be 6.5, let's put feet. A to B here, we do know the distance along this length AB is roughly 3.81 feet. And go ahead and draw a little bit of a dashed line here, because we know a couple of these angles. We know theta 1 is this angle, and we know theta 3 is the angle below that from our previous calculations. So of course, adding those together, we'll end up with, we'll call it theta 4. Theta 4 would be this overall angle here. And so, coming off to the right here, theta 4 would just be theta 1 plus theta 3. Again, theta 1 was 44.26 degrees. Theta 3 is the 23.2 degrees. And so their sum should be about 67.46 degrees. All right, so very close. Now we just need to use law of cosines, right? We know one side length, we know a second side length, we know the included angle, so law of cosines should allow us to calculate this distance between points A and C, or what we're calling the length of the cylinder here. And so Next, just implementing the law of cosines. And so here, make a note, we're going to use law of cosines. And so usually that goes c squared is equal to a squared plus b squared minus 2ab times the cosine of gamma, we'll say, the included angle. Here, there's a very good relationship that has to happen here. You've got to have the opposite angle, or the opposite side, excuse me, be opposite from the angle that's inside of the argument of cosine. And so you've got cosine of theta 4, and so then this L cylinder must be the c squared part of that. It should make sense as we walk through here. So if we follow that, it would be the length of the cylinder squared. C squared is equal to, the next part is a squared plus b squared, where a squared and b squared are going to be the sides that are bounding the angle. And so AB and BC here. I'll just write the values here. And so we'll say it's 3.81 feet squared and 6.5 feet. And then it's minus 2 times AB is the way I think of it. So minus 2 times 3.81 feet times 6.5 feet. I ran out of room there, so I'll scoot over. And then times the cosine of the included angle. That would be the theta 4, which is our 67.46 degrees there. And so the only modification really we have here is we need to take the square root. And so I'll just copy this line down here, move it up, and really we don't want this, but we'll take this and we'll raise it to the 1/2 power, or just take the square root of everything on the right hand side here. And that should get us to our new cylinder length. And so if you give me 1 second to run that through the calculator. So you got 3.81 squared plus 6.5 squared minus 2 times our 3.81 times the 6.5 times the cosine of the included angle, which is 67.46, and then take the square root of that. What I've got at this point is 6.15 roughly, and units there would be in feet. Notice at this point all of our length units have been working in feet. Let's scoot down here. The result is approximately 6.15 feet. First, it's a good idea to check kind of intuitively, does this make sense to you? Well, our original length was 5.21 feet. We're expecting the cylinder to have to raise to get longer, right, in order to raise the point D, or the cylinder to extend in order to raise point D, and so it makes sense that yes, this value got larger. And so at this point, one final step for the problem, we need to figure out the change in length of the cylinder. How much does it need to extend? And so that change in length would be delta L cylinder. It's basically L cylinder of the original, our final, and so that's this value, minus our original value of 5.21 feet. And so that's roughly 6.15 feet minus 5.21 feet, roughly 0.936. I'll just say 0.94 feet. Of course, most people don't talk about 0.94 feet. More appropriate unit would probably be inches, so we'll convert that to inches, multiplying by 12, which this is almost 11.25 inches, 11.23 inches. So the initial question that the operator would ask was, how much do I need to raise the cylinder in order to get that point D to 22 feet above the ground? And of course, after this displacement position analysis here, we're going to tell him that, or him or her, that it's going to raise 11.23 inches to be exactly at 22 feet above the ground. And so thank you for watching the video. Hope this helps you kind of get a feel for how to relate the geometries that you're given in a drawing in order to come up with your solution to your position and displacement problems. As always, thank you again for watching the video.